Hello everyone. In this lecture we will discuss about the gas phase reaction in the PEG bed reactor. So this is an example 8-5 in the book of Element of Chemical Reaction Engineering written by Fogler. So the problem is the following gas phase reaction follow elementary laws. So there are two reaction number 1 and reaction number 2. In reaction number 1, A plus 2B give us C, and in reaction number 2, 2A plus 3C give us product D. The rate law for reaction number 1 is this one: minus R1 dash into minus R1A dash is equal to K1A and to CA CB to the power 2. Similarly, minus the rate law for reaction number 2 is this one. Now, these two reactions occur in PEG bed reactor. This is a PEG bed reactor in which there is some catalyst particle in the PEG bed reactor. The PEG bed reactor is an isothermal condition. It means that the temperature inside the PEG bed reactor is constant. So, similarly, the FA0 and FB0 are entering to the uh, uh, PEG bed reactor. FA0 and FB0 are the molar flow rate of component A and component B, which are entering to the PEG bed reactor. Similarly, the molar flow rate of component A is equal to the molar flow rate of component B, which are entering to the PEG bed reactor, and the molar flow rate of component A is equal to 10 mole per minute. Similarly, the molar flow rate of component B is also equal to 10 mole per minute. The period is an equimolar in A and B. Equimolar means that the molar flow rate of component A is equal to the molar flow rate of component B, and it is equal to 10 mole per minute. The volumetric flow rate of the period is 100 dm³ per minute. So this is the volumetric flow rate of the period, and the period consists of component A and component B. The weight of catalyst is 100 kilogram. The pressure drop in the PEG bed reactor is 0.0019 per kilogram. So in this PEG bed reactor there is pressure drop, but the temperature in this PEG bed reactor is constant. So it is not isobaric reactor. The pressure drop occurs inside the PEG bed reactor. So the total entering concentration is equal to CT0. So the total entering concentration is CT0, and the CT0 is equal to 0.2 mole per dm³. The rate constant for reaction number 1 in term of component A is equal to 100. So this K1A mean this one is for the reaction number 1 and A is for component A. So the rate constant for component A in the reaction number 1 is equal to 100 dm to the power 9 divided by mole square into kilogram of catalyst into minute. So this is rate constant in reaction number 1. The rate constant in reaction number 2 is K2C is equal to 1500 dm to the power 15 mole to the power 4 kilogram of catalyst into minute. Plot. Now the question is plot and analyze FA, FB, FC, FD and selectivity of component C with respect to component D is a function of catalyst weight in the PEG bed reactor. So the question is plot the molar flow rate of components and the selectivity of component C with respect to component D inside the PEG bed reactor. So the solution for this question is there are various steps to solve this question. The solution: use the following step to reach the plots. So we will use these steps to plot the FA, FB, FC, FD and selectivity in the PEG bed reactor for the PEG bed reactor. So the first step is the step number 1 is apply mole balance on each and every component inside the PEG bed reactor. So this is a PEG bed reactor. Fa divided by the mole balance per component A is Fa divided by dW, where W is the weight of catalyst. So Fa divided by dW is equal to Ra dash. Remember that this R, the dash is for the PEG bed reactor. Similarly, the mole balance per component B is dFB divided by dW is equal to Rb dash. The mole balance per component C is this one. The mole balance per component D is this one. Now The second step is apply the net rate of component to each reaction. So to each reaction apply net rate of component. So apply net rate of component A in the net rate of component A in reaction number 1 and reaction number 2 is RA dash, because as you see that the A is present in reaction number 1 and reaction number 2. So if you see this, that this is reaction number 1, this is reaction number 1, and this is reaction number 2. So A is present in reaction number 1, it is also present in reaction number 2. B is present in reaction number 1, but it is not present in reaction number 2. Similarly, C is present in this reaction number 1 and reaction number 2, and D is present in reaction number 2 only. So you can check from these reactions. So the rate of component A inside the fag bed reactor is R A dash, and it is equal to R1 A dash. So R1 A dash, it means that the rate of component A in reaction number 1 plus the rate of component A in reaction number 2. Remember, this 2 is for the reaction number 2 and A is for component A. Similarly, the rate of component B is equal to RB dash, and RB dash is equal to R1B dash. Similarly, the rate of component C is equal to R1C dash plus R2C dash, because component C is present in reaction number 1 and reaction number 2, as you see from here. Similarly, the rate of appearance of component D is equal to RD dash, and it is equal to R2D dash. So component D is only present in reaction number 2. So therefore there is 2 in this rate. Apply the rate law given in equation. So in the question, the rate law is given to us, which is minus R1A dash is equal to K1A CA CB to the power 2 minus R2C dash is equal to R2C K2C CA square and CC to the power 3. These rate law are given to us, as you see from these rate law. These rate law are given to us. So these are the rate law. This was the step number 3. Now in step number 4, find relative rate of component in reaction. So these are two reaction. R1A dash divided by minus 1 is equal to R1B dash divided by minus 2, R1C dash divided by 1. Similarly, for reaction number 2, R2A dash divided by minus 2, R2C dash divided by minus 3, R2D dash divided by 1. Because the reactant, for reactant we will write minus, and for product we are writing plus, and these 1, 3 and 2 are the stoichiometric coefficient. So find the relative rates. Now step number 5 we will go to step number 5, and step number 5 the relative rates. These are the relative rates. We have already written it, the relative rates. So we can relate the relative rates. It means that R1B dash can be equal to R1A dash by simply rearrange this term. So this 2 will come to this side, and it will equal to R1B dash will be equal to 2 times M2 minus R1A dash. So it is equal to this one, and R1C dash is equal to minus R1A dash. Similarly, R2C dash will be equal to 3 divided by 2 into R2 dash. Similarly, R2 dash can be obtained by rearranging these term. 2 will come to this side and 3 will come to this side. So these are now net rate of reaction for species A, species B, and C and D. So there are 4 species or 4 component A, B, C, and D. So the rate of component A, the net rate of component A, which is equal to RA dash, and it is equal to R1A dash, R2A dash. And as we know from the rate law that R1A dash is equal to minus K1A into CA CB square. So R1A dash is equal to this one from rate law. You can check it from rate law. For example, this was the rate law. R1 a dash is equal to this one. Similarly, R2C dash is equal to this one from RATLA. So from RATLA you can check it. So this was from the R1 a dash is equal to this one, and R2 a dash is equal to R2a dash is equal to, from this relation, R2a dash is equal to 2 divided by 3 R2C dash. So what is the value of R2C dash? R2C dash can be obtained from the relative rate, as you can see R2C dash. So R2C dash is this one. So in place of R2C we will write this one. So R2C dash and 2 divided 2 by 3, this one. So this is the net rate of component A in the reaction number 1 and reaction number 2. Similarly, the rate of component B is 2 times into R1A dash. So R1A dash, so the R1A dash value is given from RATLA, and we will simply multiply it with 2. Similarly, the net rate of component C in reaction number 1 and reaction number 2 is R1C dash plus R2C dash, and R1C dash is nothing but it is equal to minus R1A dash, and R2C dash, this one R2C dash. Now R1A dash from RATLA, R1A dash is equal to this one, and R2C dash, the value of R2C dash is this one. Similarly, the rate of component D in reaction number 1 and reaction number 2. So in reaction number 1 there is no component D, but in reaction number 2 there is component D. So the rate of appearance of component D in the reaction number 2 is R2D dash. So R2D dash means that the rate of appearance of component D in the reaction number 2 is equal to R2D dash, and this dash is for Pike bed reactor, and it is equal to R2C dash divided by minus 3. So R2D dash and R2C dash can be related by this one. This is R2D dash. R2D dash is equal to R2C dash divided by minus 3, and this R2C, the value of this R2C dash is given in the RATLA. So from RATLA we will write its value, and we will divide it by minus 3 to get the R2D dash in order to obtain the rate of component D in reaction number 2. So this the R2C dash value is this one, and is equal to minus K2 and divided by minus 3. So minus cancel with minus. Now put equation number 5, 6 and 7 and 8 into equation 1, 2, 3 and 4. So equation number 5, 6, 7 and 8. 5, 6, 7 and 8. 5, 6, 7 and 8. Equation 5, 6, 7 and 8. 5. Equation number 5. So now we will go for equation number 5, 6, 7. This is equation number 5, 6, 7. Equation number 5. So this is the equation number 5. So this is the equation number 5. Equation number 5 is equation number 6, 7 and 8. Put these equation 5, 6, 7 and 8 in equation number 1, 2, 3 and 4. So this is equation number 1, 2, 3 and 4. So this is R A dash, and R A dash, as you can see that R A dash is equal to this one. Similarly R B dash, so R B dash, the value of R B dash is this one. R C dash from equation number 3 is equal to this one, and R D from equation number 4, this equation number 4 is equal to R2 dash, R2D dash plus R2D dash is equal to R2C dash divided by minus 3. So Now we can put the value of equation number 5, 6, 7, 8 and add in equation number 1, 2, 3 and 4. So in equation number 4, so after putting the value of equation number 5, 6, 7 and 8 into equation number 4, we will get this equation for and this equation for component A, B, C and D. So we will get, now this was step number 5, now this was step number 5. In step number 6, we will find the relationship between the concentration and flow rate. And concentration, and it is given by this relation. For component A, it is C naught Ct naught into Fa divided by Ft into P divided by P naught, where P is pressure of the reactor and P naught is the initial pressure of the reactor. And Ct naught, the value of Ct naught is given. Fb is the molar flow rate of component B. Ft is the total molar flow rate, and the total molar flow rate is equal to Fa, Fb, Fc and Fd. So this is Phi divided by Phi naught. Cc is equal to Ct naught, molar flow rate of component C divided by total molar flow rate into Phi divided by Phi naught. Similarly, this one for component D. So in step number 6, we relate the flow rate to the concentration. Now this is the isothermal reactor, so T is equal to T naught, and for the pressure changes in this fag bed reactor. So we will write the differential equation for the pressure drop in fag bed reactor, and it is equal to this one, d feed by dw, where w is the weight of catalyst, is equal to minus alpha divided by 2 phi and 2 total flow rate and the total flow rate at the initial condition. So this P is equal to phi divided by phi naught. This one phi divided by P naught can be equal to phi. This one, this P, this P and this phi. Now the parameter are given to us. Ct naught value is given to us. This value is given to us. Volumetric flow rate is given to us. Rate constant value are given to us, and the initial flow rate is given to us. The equimolar and the molar flow rate of component A was 10. The molar flow rate of component B was also 10 mole per minute. So 10 plus 10, 20 mole per minute is the Ft naught value. So after this, we will after step number 6, we will combine all step number 1, 2, 3, 4, 5 and 6. So and we will put these differential equation into the polymath or some other ordinary differential equation solver. So we will get the relationship between the time and flow rate inside the fag bed reactor. Similarly, if we are interested to find the selectivity of component C with respect to component D, so for flow reactor it is equal to Fc flow rate of component C and flow rate of component D. But when the weight of catalyst is equal to 0, then Fd will be equal to 0, because at the start the weight of catalyst will be 0, and at the start there will be no product in the reactor, so it will be equal to 0. So it will be equal to 0. Now if we put 0 in this place, it will be equal to infinity. So it will be equal to 10 to infinity. Now so if this value 10 to infinity, then it will crash our polymath. So we will set the value of selectivity between 0 and very small value of catalyst, like 0.0001 kilogram, to prevent polymath from crashing. So the condition, we will put the condition in polymath, and the condition function is like selectivity of component C to D is equal to if W is greater than 0.0001, then give us Fc divided by Fd, otherwise else give us 0. So if W is greater than 0.001, then Fc divided by Fd means selectivity will be given to us, by polymath, otherwise polymath will give us 0 value if W is less than 0.0001. So this was all about the fag bed reactor in the fag bed reactor, the gaseous reaction in fag bed reactor. So in the coming lecture, we will use polymath to solve these equation. We will solve these equation in the polymath in the coming lecture. Thank you very much for your attention. If you are new to the channel, please like and subscribe.